Alexis, you're back. I didn't scare you away.
No, you didn't.
Awesome. All right. Well, let me try harder. One thing that we talked about in the previous video was about pointers and how to make pointers point to different variables. But did you know that we can make pointers point to a variable without even creating a variable for it to point to?
What?
Yeah, that's correct. We can dynamically create variables using pointers.
How do you do that, Dave?
The way you do that is you are going to use a new keyword called new.
Ooh, fancy.
And so what new does is new basically allocates memory of whatever we tell it to. It's going to allocate it, right? But we need a pointer to be able to do that. Now the problem with allocating memory is when we allocate memory dynamically, right? Meaning that we do not do that. We only do that using pointers, right? We use pointers to go and find a place in memory, in the static memory. Uh, Sorry, not in the static memory. It's going to do it in our free store, which I'll talk about in a second. Um, when we allocate memory in the static memory, right? That's when the compiler does it. The compiler manages that memory. And remember I said in another video, the compiler knows when to actually delete that variable when the life of that variable is over. However, when we use dynamic variables, the compiler has no idea when the life of that variable is done.
So then, how do you release the allocated memory?
That's a great question. I'm glad you asked. New is not single. New has a spouse.
A spouse?
Yeah, new has a spouse. Yeah, this is probably one of the few keywords that actually have are in a committed relationship. Would you like to meet new's significant other?
Of course.
All right. Well, I would like to introduce you to delete. And guess what delete does?
It releases the allocated memory.
Absolutely. Yes, it will deallocate the memory. And so they are a jealous couple. New and delete are a jealous couple. And so if you're gonna use new, then delete demands that you use delete as well.
Are there any instances where that's not true?
There is no instances where that's not true, right? There can be a time where we use delete, we use new, and then the program ends. And when the program ends, of course, everything gets deleted out of memory. But we never want to do that. You know why?
Why?
Because that's bad practice.
Bad
It's
practice.
bad practice. So we always want to make sure that when we use new, that we use delete, because what will happen is we will deallocate memory and never free that memory up, right? If we allocate memory and never free it up, what do you think will happen? If we continue to allocate memory and never deallocate it,
Shit's gonna go bad.
shit is going to go bad. Absolutely. We are going to run out of memory, right? Our computer only has so much memory that it can use, right? I mean, if you have a really, really powerful computer, you have 16 gigabytes of memory, but that can get used up very, very quickly. So let's talk about how we would allocate memory, right? So inside of our previous video, we talked about pointers, right? And so we can create a pointer simply by using the asterisk. And this actually tells us that this variable is now a pointer that can point to integers. But not only is it a pointer that can point to integers, it is actually a variable that can create integers in the free store, meaning that we can create an integer in a memory without having to say something like int x equals 5, right? We can do that without saying int x equals 5. So how do you think we do that?
Maybe you could do int pointer equals new int?
Absolutely. If we want to create a new integer, right, we just say int pointer equals new int. Absolutely, right? Because as we see here, new means that it allocates memory. So what this pointer is doing is now finding some memory address and putting a new integer there. Well, that sucks because I don't have a name for that integer. So how do I make changes to that integer?
The dereference operator.
Absolutely, our dereference operator. Our dereference operator will say that we can set that value of that new integer to 5. We can change the value. So let's just kind of look at what's happening in the memory. So in my previous video, we had a little convention like this where we have name, we have value, and we have the address. Right, so when we create our pointer, right, let's say our pointer gets created at address 5000. As soon as we use the new keyword, we're gonna go and find a place in memory to hold space for an integer, right? We said new integer, so we're gonna go find a place for a new integer. But we didn't create an identifier for it, right? So we don't really know what the name of that variable is. But what we do know is that, you know, it has an address and it's able to hold a value. So this pointer is now pointing to this new integer that it dynamically created. So what does that mean for the value of this pointer?
The value would be the memory address of that new integer that you created, which would be 1000.
Yeah, that's absolutely correct. That would be 1000. So now, even though we don't see that variable that it created, it did create this variable inside of the memory, and then it also made it so that it's pointing to that new variable that it made. So let's demonstrate why delete is so jealous of new and wants to make sure that it's always there. So let's go ahead and do let's make an example. So let's say I create a for loop. All right, and let's say inside of my loop, I'm going to say pointer is equal to a new integer. So let's just kind of trace that, right? So here's pointer. Right now it's pointing at this, whatever reallocated. So now what happens when I is equal to 0? What happens when I is equal to 0?
You create a new integer in memory.
All right, so I create a new integer in memory. And then let's say that's at 1001. And then what happens to the value of pointer?
It gets changed to whatever that integer's address is.
All right, so that means that this value here is going to change to the new variable that it created.
Yes.
So that means that we're going to go ahead and change this to 1001.
Yes.
All right. Now, what happens when I is equal to 1?
It goes heads and creates another integer in memory.
All right, so it creates another integer in memory. And let's say that this time it puts it at 3007. So then what happens to the value of pointer?
It's going to change to 3007.
Yeah, it's going to change to 3007. And we don't need to go through 5 times to see what's happening, right?
Yeah.
So what do we see happening right now?
What's happening is that you keep allocating space for these integers, and then there's no real way of going back and like deleting or deallocating that memory.
That's correct. There's no way to go back, right? Because the pointer can only hold the value of one address, right? Because it's only pointing to one address. And then when we change that address, then we no longer are pointing to the previous thing that that pointer was pointing to. So what does that mean for this, all this good stuff? What does it mean for these two variables?
They never get deleted.
Yeah, they just stuck in the memory, right? So when we loop through 5 times, oh, big deal. But what if we decided that we were gonna loop 5 million times? And
Your computer's gonna break.
the computer's probably gonna break. Yeah, it's not gonna be very happy about that, right? So that's why delete says, hey, if you're gonna ever use my spouse, then you better make sure that you use me as well, so we can prevent that. And so how do you think we use the how do you think we use delete?
I assume right after that pointer equals new int statement.
So okay, so we could put it there. We could put it there. So how do you think we write that? What do you think the syntax is for deleting a pointer?
Maybe just delete pointer.
Yeah, absolutely. We just say delete and then the name of our pointer. And so what happens now? So let's actually just kind of back up, right? Let's go back to 0 is equal to 1. Let's go ahead and start all over again. And let's trace this algorithm. All right. So now let's say 0 is equal to, I'm sorry, I is equal to 0. So what's going to happen first?
You're gonna create your integer
We'll
in
create it.
memory.
And let's say it does it at 1005. And then what happens to the value of pointer?
The pointer's value goes to 1005.
Absolutely. So we have 1005. Then the next thing that happens is we call delete. So that means that we are going to now deallocate this memory, right? So just for demonstration purpose, that means that we're going to go and say, hey, you know what? This memory address is now free. You can go assign another integer there or another variable. This memory address is open for business,
So does
right?
that mean that pointer is pointing to nothing?
So that's a great question. It means that pointer is still pointing to this address, but it's now pointing to an address that is not reserved.
Is
Meaning,
that it doesn't have a value?
not that it doesn't have a value, but it means that it's not reserved, meaning that that memory address is up for grabs.
Okay.
Yeah, so that means that we really no longer have control of that pointer because it's up for grabs. It can get changed to whatever by something else, and we have no power over that. So it's just basically freeing up that memory address.
Okay.
All right, so what happens when x is equal to 1? I mean, sorry, I is equal to 1.
You create a new integer in memory.
Create a new integer in memory, right? So we'll go and create one here. Let's say it goes to 3001. And then what happens to pointer?
It gets changed to 3001.
Absolutely. And now we call delete, and what happens here?
The integer that we just allocated gets freed up so anything can use it.
Yeah. So with that said, do you think that this is kind of useful? What's the point of us creating a variable and then deleting it right away?
I don't think it's very useful.
Yeah, it's not very useful. It's not very useful. So usually you want to make sure that when you create a variable, you create it for a reason. You use that variable for whatever reason you needed it for, right? You recognize when that the life of that variable. You recognize when it's time to kill that variable, right? Just as the compiler knows to do it when we get to the end of a scope, you have to figure out when the scope is complete. And then at that time, that's when you actually call your delete.
Yeah, that makes a lot of sense.
All right, so that's so those are the happy couple, new and delete. Now let's talk about let's get a little let's get a little crazy, right? We can create one integer, but so what? Why do I need a pointer to create an integer? Why don't I just create a damn integer and call it a day?
Is it possible to do it with arrays?
Absolutely. We can do it with arrays, right? We can do it with arrays. And let's just talk about arrays for a second, right? Let's just talk about arrays. We love arrays, but we also kind of hate arrays, right? Why do we hate arrays sometimes?
Because they need a definite size.
Because they need a definite size. Yes, we need it's a fixed size.
Big size.
What else?
Um, it's really hard to insert. Can you insert into an array?
You can, right, with partial arrays, right? You need partial arrays to be able to insert.
Nothing's really coming to mind about why we hate arrays.
Oh, why we hate arrays? All right, so fixed size is a really big one. What about what about you know wanting to use an array in a function?
You can't. You can't really use it. There's no. You can't really return arrays, so you
Yeah,
can't like change the value within the array without, I'm assuming, needing a pointer.
yeah, absolutely, absolutely. What happens if we have an array and we the array gets bigger than we expected?
Then we start going into memory that is not ours.
Yeah, yeah. So we can definitely get out of bounds easily, right?
Yeah.
But also, if we were really careful with the managing our memory, if we got out of bounds, right? If we have more items than we need, right, than our array can hold, then what we have to do is we have to create another array, right? We have to create another
Oh,
array,
resizing.
resize it, right? And then copy everything over to a bigger array, right? And that's going to be really hard to manage inside of your program because now all of a sudden this name has an identifier, this array has a identifier, right? And now we get a new identifier for this array. And now we have to write our code so it says, all right, if it gets bigger, then we're going to change the name of our array. And we can do an example of that and see how it's going to be nearly impossible to do. And it's going to make you, if you have a lot of hair, you're going to lose a lot of hair trying to trying to do something like that.
A lot of tears.
A lot of tears, absolutely. So we can fix that by doing dynamic arrays. Like you said earlier, yes, we can actually use our pointers to dynamically create arrays. We don't just need to be able to create integers. So let's talk about that. So how do you think we would create a new a new dynamic array using our pointer?
Well, I would assume that perhaps you could point your pointer to an array that's already created.
Okay, so let's do that. So let's go ahead and create an array. So let's say we have our int array. So then how do I want to, how would I point, well, let me tell you, how do I point my pointer to this new array?
I think you can do p equals the array.
P equals the array.
And if not that, then p equals ampersand array.
All right. So the question is, will it be P equals array or is it P equals ampersand array? So let's talk about that. What is actually an array? So when I create this variable array, this of size 5, Does this variable actually have 5 integers inside of it? Is this big variable that's holding 5 integers?
No.
What exactly is an array then?
Isn't an array just an address?
Array is nothing but simply an address, right? It's an address, and what is that address representing in that array?
I think it's the first index of the array.
Absolutely. We have our memory here. I'm just going to use N, B, and A for short. We have our memory here, and we create array. When we say array 5, it is going to block up 5 memory addresses, right? But the value of the array is nothing simply, it's just simply the address of where the first index is, right? It's just simply the address. So if that array starts at 1000, then it's the value of that array is 1000, right? And you can if you don't believe me, you can see out an array, right? When we see out an array, we would love for it to output the content of the array, right? But we know that when we see out an array, we actually will get the address.
Is that the address of the actual array, or is that different?
It is the address of consider an array the same thing as a pointer, except for an array is static. They actually work the exact same way. They are really they really are the same thing. They can be used exactly the same way.
Okay. So if you wanted to get the actual address of the array, then you would do the ampersand array?
If you want to do, yes, if you want to get the address, this is going to give me the actual address of the array, not the address of where the array begins. Absolutely.
Okay.
So this right here would not be the right way to do it. Since a pointer can point to an address, right? The value of a pointer can only hold addresses of variables, and that is what an array represents, then this would be the correct way to point a pointer to an array.
Awesome. That makes sense.
All right, great. So that's one way to have a pointer point to an array. What's another way to have a pointer point to an array?
I'm assuming since you emphasize so much on new and delete, that there's probably some way to do it that way.
You guessed correctly. There is a way to do it. So if we want to do a dynamic array, we can do so by creating a pointer that can point to integers, right? So that means I'm going to say integer and then my pointer. And then we're going to have it equal a new integer array. And then we'll put in our size. And so now what that does is it's going to do the exact same thing in our memory. We're going to create a pointer. Right, the pointer is going to find 5 slots inside of the memory. And let's say we start at 1000. So that means the value of the pointer is going to be what?
1000.
The value of the pointer is going to be 1000. And we can just say the address is at 5000, right? And so now our pointer looks exactly the same as if it was now a regular pointer. So how does that work? Why is it's still pointing to one value? So how are we saying that this is an array now? How are we saying that this pointer is pointing to an array when it's still just pointing to one address?
Because it has those 5 slots already allocated.
Yeah. So the thing is, all it did was allocate the memory. It just reserved this space, but it is still just pointing to the beginning of that array, right? It just wants to know where the beginning of the array is. It doesn't need to know where the remaining part of the array is because our index take care of that, right? The indices of the array will take care of that. If I want to get index 0, then I will get the value of my pointer, right? Which is an address, right? I'm gonna add my index, which is 0. So let me just label that address, index, right? And then that's gonna be the address that I go to, right? So if I'm saying pointer 0, then I'm really saying address 1000 plus 0, and then I'm going to that address, which is going to be the very first address of my array.
So how would you translate that into code?
How do I translate that into code?
Yeah.
So I'm glad you asked that. So we can use the square bracket notation on our pointer. However, we won't be doing that in this class. We are going to do it the old-fashioned way, right? The old-fashioned way says that we are going to dereference our address and add the value, right? Just like we said here. So if I want to find the address for, let's say, index 3, whoa, that was weird. If I want to find the address for index 3, which is, what is the address for index 3?
1003.
1003. Then I need to dereference pointer to figure out where 0 is. And then I need to add the index, right? So I want to dereference P so that I get 1000. Then I want to add my index, which in this case is 3. I probably should just, right, that's my index. So if I dereference my address and then add 3, what would I get here if I was to do it this way?
I think you would get an error.
I will not get an error, but I'm not going to get the address that I want. And
No,
why do you say that I'm going to get an error?
I think you're not supposed to have that dereference operator.
Not the dereference. Okay, so you want me to say P plus 3? You're saying that will give me my address?
Yes.
Yeah, that would actually give me 1003. Now, what if I wanted to change the value? So it's great. Now I have the address, but now I need to go and change the value at that address. So how do I use that? What do I do?
I think you would put all of that P plus 3 in parentheses and then use that handy dandy dereference operator.
You're absolutely right. Right? If this is going to give us an address, then we want to, in order to change that value, we need to dereference that address and then go and change the value. So if I want to change this to 10, then that's the way I would do it. So remember, this is going to be my address. I'm going to dereference that address, right? So I'm going to go and find the value of P. I put P, but let's just pretend that P is representing PTR. I'm going to find the value of P, which is 1000. I'm going to add 3 to it so that I can get 1003. So now inside of the parentheses, it says 1003. Now I can dereference that address, meaning that I'm gonna now go to that address in the memory, and then I can go and change that to 10. And so that is basically the way arrays work, and that is the way dynamic arrays work. So then why use dynamic arrays? What's so special about them?
Probably the ability to resize.
The ability to resize, okay? And so if I want to resize my array, my dynamic array to, let's say, size 6 rather than 2, can I just do this? Oh, I'm sorry. Can I just say PTR 6? Would that make it bigger?
No.
What does this actually
um, it goes out of bounds.
do? It will. That's absolutely correct. It goes out of bounds. This is not something that we're able to do. So then how would I make my array grow then? How can I make it resize if I can't do that? Do I have to do something like this? Do I redeclare it? Whoops, sorry.
Not quite, but you would have to create a temporary pointer of
Okay,
whatever size that you would want it to be.
okay, so this isn't gonna work either. And why doesn't this work?
Because it's gonna eliminate all the data that you already have inside of the pointer, or it's just gonna give you a bunch of errors.
Yeah, this could be an error. I can't redeclare another variable with the same name, right? I can't do that.
Yeah.
So yeah, you said that you're absolutely correct. We would need to create a new temporary array. So I'm gonna go ahead and do that. Okay, so now I have a new temp array. So how does that resize? How is that resizing my pointer?
Well, you would you would first have to create the temporary array as you have done,
Okay,
and then find a way to copy all the values from your original array, original dynamic array, and shove them into that temporary array.
okay. So how can I do that? So if I want to just copy everything from pointer into temp, can I just do this? Would that work?
No,
Why?
no.
What is this doing?
It's basically having two pointers pointing at the same dynamic array, which is a big no no.
Big no, right? We just now lost where this pointer, right? We lost all this memory that just got allocated by doing something like that. So we can't do that. So then how do I copy everything from pointer over to temp if I can't just say temp is equal to pointer?
You would need a what I call a walker, I guess.
A walker? Okay.
Yeah.
And how do I, so what do you want me to do?
Create a int pointer walker and set that equal to the original pointer.
Okay.
Yeah. And then you would probably want to iterate.
Okay.
So, um, yeah, so for int I, or no, for, well, I haven't done this in a while.
What do you mean you haven't done it in a while? You're just not learning this, Alexis.
I
Yeah,
think I might need your help on this one.
yeah. So yeah, you're absolutely right. We probably don't actually even really need to do this walker. We probably don't need the walker. But yeah, what we want to do is say int I is equal to 0, while I is less than the original size, right, of our old one, which was 5, and then I plus plus. And then we simply just want to copy it over, right? And we're going to do our ugly way of doing it. We're going to say star, right? PTR plus I, right?
Wouldn't
That
you
means
do
that,
temp?
oh, you're absolutely correct. Yes, temp plus I is equal to what?
Star and then pointer plus I.
Pointer plus I, right? So what that's doing is saying, let's go ahead and find the address that temp is pointing to, which is the first index in this new dynamically allocated array. And then we're gonna start from 0 and we're gonna find the address plus 0, dereference it, and then set it equal to the address that pointer is pointing to plus 0 and dereference that. So the value at this address is gonna be set to the value at this address. And we're gonna keep looping that through until we get all the values from this pointer copied over to this new pointer. Right? And so this is equivalent, right? We could just say temp I is equal to PTR I. These are actually doing the same thing. But until you understand this notation, I do not want you to use this notation, right? Until you can look at this and it doesn't look like madness, then we're gonna go ahead and use that. So this is gonna be off limits for now. All right, so now that we copied everything over, well, I don't understand. Now I have two pointers, I have two arrays that now have the same values in it. How did that make my array resize? Right? Because now temp has everything that pointer had in it. But that's not resizing my array. That just gives me two arrays. So
So now what you would do is you would delete pointer,
all right.
but in while deleting it, since it's an array, you would have to use the brackets after the delete, the square brackets.
Okay, so I do square bracket. And then what do I write?
Pointer,
Pointer. Well, why did I need this square bracket?
because it's an array.
That's weird. I don't have to put a number in that square bracket. That's weird. What's going on with that?
It just deletes the whole entire array.
Yeah, that's absolutely correct. The compiler doesn't know when to do the deallocation, but when you use the bracket, it at least knows how much memory was allocated by this pointer. And so if you want to delete every memory address that this pointer allocated, as far as when it actually did the array, sorry, it's way up here. When we first allocated memory, the compiler will know that this pointer allocated 5 memory addresses. And if we want to delete all 5 memory addresses that this pointer used when it called this new keyword, we have to use the brackets. What would happen if I didn't use the bracket?
It would only delete the first memory address, and
Absolutely.
it would leave all the other ones within I think the free store.
Yeah, absolutely. If we don't use the bracket, it's going to basically say, hey, all right, let me go to pointer. Let me see what address it is pointing to. And then I'm going to go ahead and free up that address only. And it frees up this address and it leaves all the remaining addresses here. But if we use the bracket, right, if we go down and we say, let's use the bracket, then it's going to actually come to pointer and it says, hey, pointer's pointing at address 1000, but it allocated 5 memory addresses. So we're going to start at 1000 and we're going to delete all 5 of them. And so that's what the bracket is doing. Awesome. So now we know how to delete our pointer. Well, whoa, wait a minute. That's not resizing. Now we have a temporary pointer and we don't have our old pointer anymore. Well, that's not resizing.
Well, I mean, the last step would be to set your original pointer equal to the temporary pointer.
All right, so if I set the new pointer equal to the temporary pointer, what does that mean?
It basically means that your original pointer is now pointing to the new array of size 6 that was allocated.
Absolutely. And so now there's an extra space memory and we're using the same address. When we continue inside of our code, we don't have to now change our code to our variable to a new name, right? We can still go on using our identifier pointer to access our variables. And so that gives us the illusion that our array grew in size.
Yeah.
Doesn't that kind of remind you of something that we learned in CS2? What does that remind you of that we use in CS2? Didn't we, there was this one kind of array that we like to use better because we didn't have to declare size and we could just start adding things and it would just grow in size as we added. What was the name of that data structure?
A vector?
Yeah, that's right, a vector. That's right, a vector. That's exactly how vectors work. Vectors look like they're just growing in size, but what they're really doing is they're using dynamic arrays and they're pointing pointers to different places in the memory as needed.
Wow, I didn't
So
know that.
yeah, good. I didn't know that either. I just made that up. No, I'm just joking. That's exactly how vectors work. So any other questions about dynamic arrays?
No, I think you answered all of them.
All right, well, thank you. And I'll see you later when we talk about multi-dimensional arrays, unless, of course, you are fed up with me. To be continued. Dun, dun, dun.
Done.